Welcome to Study Loop.
This question is definitely a marathon question for a reason. It is a good 8 questions that are that are very difficult all by themselves. It describes impure nickel being refined by smelting sulfide ores in a blast furnace. It can then achieve pure metal close to somewhere between 99.90 and 99.9% nickel through the Mon process. The primary reaction is nickel, impure, reacting with carbon monoxide, creating nickel with 4 carbon monoxides. When this process occurs in the forward direction, we pull out just the nickel, leaving behind any of the impurities. Then if we can force this reaction to go, instead of in the forward direction, in the reverse direction, then we can deposit pure nickel because none of the impurities would be found in this gaseous species. Part A wants you to, without referencing Appendix 4, predict whether or not delta S standard for the above reaction is positive or negative. Well, as you recall from the chapter, to predict whether or not delta S for a reaction is positive or negative, we need to look at the number of moles of gas. If we are producing more moles of gas, we are increasing entropy. If we are decreasing moles of gas, then we are decreasing entropy. So we are going from 4 moles of gas to 1 mole of gas. So order has increased and entropy has decreased. So the sign for delta S system, this being the system, would be negative. Then for part B, it says the spontaneity of the above reaction is temperature dependent. So predict the sign on delta S surroundings for this reaction. Well, for it to be temperature dependent, then we need to have it spontaneous in one direction at, say, high temperatures or low temperatures, and then spontaneous in the opposite direction at the opposite extreme of the temperature. This is not necessarily important to answer part B. What is important to answer part B is understanding the relationship between delta S universe, delta S surroundings, and delta S system, and to recognize that for any reaction, any process that is occurring, delta S universe needs to be greater than 0. So if this process is occurring, delta S universe is greater than 0. Delta S universe is equal to delta S system plus delta S surroundings. So if delta S universe is positive, greater than 0, with delta S system being negative, then delta S surroundings must be positive positive and more positive than delta S system is negative, so that the sum will give us a positive delta S universe. For part C, they give us the delta H standard of formation of the nickel species and the delta S standard, and they want you to, using values from the appendix, calculate delta H standard and delta S standard for this above reaction. Well, as you recall, the delta H standard for a chemical reaction is going to be the delta H of formation of the products minus the sum of the delta H of formation of the reactants multiplied by the corresponding coefficients. So there's a coefficient of 1 on the NiCO4, and it has a delta H of formation of negative 607 kilojoules per mole. We will then subtract off the sum of the delta H's of formation of the reactants. The delta H of formation of nickel is 0, and the delta H of formation of carbon monoxide is negative 110.5, and we'll multiply that by the coefficient 4. This then gives us a delta H standard for the reaction of negative 165 kilojoules. Delta S standard is going to be the same thing, but we'll use delta S values instead of delta H values. We'll take the delta S of the product, which is provided at 417 positive joules per Kelvin mole, and then we'll subtract off the S standards for the reactants. The S standard for carbon monoxide is positive 198 joules per Kelvin. There are 4 of them, so we'll multiply it by 4 and then add on 1 times the S standard for nickel, which in the back of the book is 30 joules per Kelvin per mole. This then gives us a delta H standard for the reaction of negative 405 joules per Kelvin. Okay, for part D, it wants you to calculate the temperature at which delta G standard for the reaction is 0. To do this, we recognize that delta G is equal to delta H minus T delta S, and we want to figure out the temperature at which this is 0. So we'll plug in 0, we'll plug in our delta H value, and we'll plug in our delta S value. However, when using this equation, we need to make certain that we are in the same units. Up here we're in kilojoules, and down here we're in joules, so we either need to convert this to joules or this to kilojoules. I chose to convert the delta S into kilojoules, 0.405 joules per Kelvin. Then we can rearrange this equation and solve for T, and T becomes 407 Kelvin. As you recall, when delta H and delta S both have a negative sign, then the reaction becomes spontaneous at low temperatures in the forward direction. And in part E, this is what is being described. The forward direction occurs at a low 50 degrees Celsius, while the reverse of the reaction occurs at a high 227 degrees Celsius, as explained in part F of this problem. So for part E, it wants you to calculate the equilibrium constant for the above reaction at 50 degrees Celsius. As you recall, delta G standard equals negative RT natural log K. Rearrangement of this equation gives us the equilibrium constant is equal to 2e to the negative delta G standard over RT. Well, delta G standard is going to be delta H minus T delta S, but when using this equation with an R value of 8.314 joules per Kelvin mole, everything needs to be in units of joules. So we'll take our 165 kilojoules, multiply it by 1,000 and get joules. This will be our delta H value. So right now I'm calculating delta G. This will be delta G, and I'll do negative delta G standard. Delta G is going to be delta H minus T, which needs to be in Kelvin. 50 degrees Celsius plus 273 puts it in Kelvin, multiplied by delta S, and I'll keep it in joules because I just converted this to joules. So this is negative delta G standard. I'll then divide by R, 8.314, and T, the temperature is 50 degrees Celsius, but everything needs to be in Kelvin, so I add on 273 down here also. This gives us an equilibrium constant of 3.4 times 10 to the 5th, suggesting this reaction goes to the right at 50 degrees Celsius. It goes in neither direction at 407 Kelvin, and 407 Kelvin is 100 and, what would that be? 134 Kelvin. So at 50, it goes in the forward direction. At 134 Kelvin, or 134 Celsius, or 134, hold on a second, at, let's see, where was I? At 50 degrees Celsius, it goes in the forward direction. At 407 or 134 degrees Celsius, it goes in neither direction. And above 134, it goes in the reverse direction. This is what we're going to talk about now in part F. In part F, it simply wants us to calculate the equilibrium constant at 227 degrees Celsius. So it'll be the exact same calculation that I performed before, but instead of putting a 50 here, I'm going to put 227. This will give us the delta G standard. I'll then divide by R and T, and again I'll put 227 here instead of 50. And based upon what we were discussing, we should get an equilibrium constant that suggests equilibrium to the reactant side, shifting this reaction to produce the solid nickel. And sure enough, we do get a small equilibrium constant, 1.2 times 10 to the negative 4, suggesting at 227 degrees Celsius, the reaction shifts back to the reactant side. Part G wants to know why is temperature increased for the second step of the MON process. Well, this is simply what I was mentioning before. In the first step, we want to form the nickel species from the impure nickel solid, and that occurs at 50 degrees Celsius. Then we increase the temperature to 227 degrees Celsius so that it shifts back towards the nickel side, and in the process deposits pure nickel. So that's why the temperature is increased, to reverse the reaction and deposit pure nickel. Part H is a whole challenging problem all by itself, and it's the last part of this question. It says that occasionally the temperatures increase to 152 at higher pressures, and it wants to know how high of a pressure can you go to before liquefying the NiCO4. So the equilibrium would be the liquid going to the gaseous state, and the equilibrium constant would describe the pressure of the gaseous nickel compound. And then as a hint, it says if the pressure is greater than the equilibrium constant, then it's going to liquefy. So we simply need to solve for the equilibrium constant. Okay, we know that delta G equals 0 at a phase change. This is a phase change. So knowing the temperature and the delta H for the phase change, and the equation delta G equals delta H minus T delta S, we can calculate delta S. This is what we are missing right now, delta S standard. So, let's solve for delta S first at the phase change temperature. Phase change temperature is 42 degrees Celsius. We'll add on 273 to get it in Kelvin, and we know delta H for the process that was provided. So we'll get delta S for the process of 0.0921 kilojoules per Kelvin. Okay, now we need to make the assumption, as we did before, that delta S standard and delta H standard do not change their values significantly with temperature. And we can calculate the equilibrium constant, which will correspond to the maximum pressure, by taking our negative delta G, similar to what we did before, where delta G is delta H standard minus T delta S. Well, the temperature is now not 42, but rather 152. So we'll add on our 273 and then multiply that by the delta S standard that we just calculated. Now when using this equation, everything needs to be in joules, so I'll convert my 29 kilojoules into joules, and I'll convert my 0.0921 from kilojoules into joules, getting 92.1. So this then, all of this is delta G standard. I'll then divide by R, and the T, the temperature we're now considering, is 152 plus the 273, and I get 2.87 bar. When using this, it really comes out as bar instead of atmosphere, but bars are very close to atmosphere, so we could approximate this as 2.87 atmosphere if you would like.